Well, this is both a sad and a happy day. It's a sad day because it's the last day of class for EE 637. But it's a happy day because it's the beginning of the rest of your life. And also, it's a happy day because I brought little candies in for you to celebrate the end of the semester. See? Now, for the people on TV, I apologize. It's not going to be exactly the same for you, okay? But you're in our thoughts, okay? So here we go. And for anybody who doesn't come to class, well, it's just too bad for those guys, right? Here you go. Here, you want to take that bag over here? And I'll pass.
Shall we clap?
Excuse me?
Shall we clap?
Oh, sure. Thank you. There we go. So I thought, I'd cover maybe a few things today, a little bit less structured. I'd do a little bit of the JPEG for the people working on the labs. Also, I can answer questions for people who are working on the labs, particularly the JPEG lab, and or I can answer any questions regarding material that, like, for instance, will be on the exam, or any other technical material. So, how's the JPEG lab going?
Done.
Okay?
Yeah, already done.
You're finished?
Yeah.
Oh, fantastic.
Finished.
How many people are done?
I finished at 3:30 in the morning.
Really?
A significant number. My ears are clogged. I was flying today. Okay. Let me just, I think you probably, hopefully you've understood the basics of JPEG by doing the lab. And also you have to read the introductory material that describes it. But let me just kind of go over that as a review. I'll describe some of it. So if we can switch to the tablet. So basically, the flow, oh no, not the computer, the tablet, I'm sorry. Yeah, so the flow is that you take, the way JPEG works is you take the image, you break the image up into 8 by 8 blocks, right? And then, let's do a few more of these. Okay, and then you take one of these 8 by 8 blocks, okay, and you take a DCT, discrete cosine transform. Then you get an array of pixels. Let's say that there's different ways you could organize the DCT, but let's just assume that this pixel here is 0, 0. Let's say that's the 0, 0 pixel. So this is the DC coefficient, right? And then actually what happens is that this is the highest frequency. So this is the highest vertical frequency. Vertical frequency. Okay? So if someone has, if in that block you have a lot of stripes like this, right? There are a lot of horizontal lines, then that energy will map to this location right here, right? And if you have a lot of vertical lines, that'll map to that location right there, okay? And over here, that maps to actually something which is basically a checkerboard. So it would be like plus, minus, plus, minus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, like that, okay? So, and then this is DC, okay? Now, the thing about, okay, then once you do that, then what you do is you quantize. Now, which frequencies are most important? The high frequencies or the low frequencies?
Low frequency.
Why?
Human visual system is a low pass filter.
Because the human visual system has a modulation transfer function, right? See, this is where we're pulling everything together. So somewhere around, say, 11 cycles per degree, it starts to drop off. Actually, it's not low pass, it's band pass, but we'll just approximate it by low pass like that. So what ends up happening is these frequencies are less important, right? Higher frequencies are less important. So that means you can quantize these more coarsely. So the DCT, if properly normalized, is an orthonormal transform. Since it's an orthonormal transform, if properly normalized, using conventional normalization, it's not orthonormal. It's just orthogonal, but not normal. But it's easy to adjust for that. You just divide by some appropriate constant. I think it's something like the square root of n. But in any case, what happens is that if you had uniform quantization, so all the values are quantized with the same step size, then you would be minimizing the mean square error distortion. But you don't really want to minimize mean square error distortion. You want to weight the high frequencies are less important. So you want a larger quantization in the high frequencies and a smaller quantization in low frequencies. So what you do is you take the DCT, you take DCT of ij, you divide it by, I think I call it Q of ij, right? And then you, Q is a number which grows, this is the size of the quantization step, right? And then you round. Round. And that performs quantization. And that'll give you like a K of ij. It'll actually give you an integer value at each ij. And that's the value you encode. When you decode, then, you just take K of ij and you multiply it by Q of ij. And that produces your estimate of what the DCT was. I'll put a hat here because it's not the true DCT. It's an approximation after quantization. But the basic idea is that Q is larger for higher frequencies, right? So from here you quantize, and now what happens is after you quantize, a lot of these values are non-zero, but a lot of this is zero. You might have some individual non-zero ones out here. So what you then do is you use zigzag coding. You go like this, and you run length code the zeros in a zigzag. And the reason you use a zigzag is because remember that the boundary of constant frequency is sort of like a circle here. So you do best if you sort of if you did it like this, you would then stop getting runs when you hit this region here, right? So you tend to do better if you do the run length coding this way, which is how the standard's specified. So you do run length coding this way, and now the DC coefficient you code separately. The DC coefficient is differentially coded. So let's say that this is block L, right? So you take DC of L minus DC, I'll say hat, of L minus 1. And that becomes the differential value, delta DC of L. And that's the differential value. You code the differential value, and then you reconstruct it to get the DC hat. So you basically, you use the decoded version of the previous DC coefficient and you subtract that off. There's no point in coding that again, because the DC values of nearby blocks tend to be similar. the AC coefficients, it's not worth doing that. There's not enough redundancy to make it worthwhile. Those you just quantize individually. And then you do, after you do the run length coding, and there's this VLI, VLC stuff, which I won't even try to explain, but you can read about it. It's variable length, number of coefficients in each of the quantized values. And then what you do is you do Huffman coding of that information, and then you send it on its way. And the decoder reverses all this. So you're going to actually do this you're going to program it all up yourself. So when you're finished, you'll understand it completely, right? Now, yeah, I see some smiles. Okay, so now what's going to happen? One thing you might say is, why do we use a DCT? Well, why do we use a Fourier transform anyway? Okay. Well, it's a magical thing. It turns out that if you take, okay, I don't know how much detail to get into this, but I'm going to just, if you don't understand this, it's okay, but I feel an obligation to at least state it, okay? If you have a random process, okay, a stationary random process, so you have, let's say x of n, this is stationary, say Gaussian, doesn't have to really be Gaussian random process. Key thing is that it's stationary. Okay? If you take, remember when you did the lab on power spectral estimation, you took the Fourier transform of x, and it looked pretty noisy, right? And if you make a longer sequence x and you take its Fourier transform, it still looks noisy. Well, it turns out that the Fourier transform, if you take the Fourier transform, Fourier transform decorrelates xn. Decorrelates so that's true for any xn that's a stationary random process. And basically, the reason the Fourier transform decorrelates xn is the same reason that the Fourier transform turns convolution into multiplication. And it's a little too complicated to go into. But basically, how many people know what a Carhoon-Loeb transform is? Okay, so everybody knows what principal components analysis is, right? Because we did that, right? So if you have, let's say you have a vector, the expected value of x transpose equals r, right? So, and then r here is equal to e lambda e transpose, right? We all know that because you did the lab, right? And if you say x tilde equals e transpose x, right? So, it turns out then, if I compute the expected value of x tilde transpose, what's that going to be equal to? This would be a good test question. You should be able to actually, you can calculate it, and I will maybe if you want me to in just a moment, but you should be able to basically understand that off the top of your head from the lab. It's asking a lot because I understand that you haven't done that. Okay, ideally, if you really understood the lab well, you'd be able to just tell me right now what this answer is.
Lambda.
It's lambda. Oh, wow, I'm really impressed. Okay? Because the eigen decomposition, what you should have learned from the lab, if you didn't quite get it all, don't feel too disappointed because it takes a little while for this to sink in, okay? But really the moral of the lab, okay, the takeaway concept, the big idea of the lab was that the eigen decomposition decorrelates the data, right? So lambda is diagonal. So not that each element of x tilde doesn't have the same variance. Some of them have larger variance and some of them smaller, but that's equal to the eigenvalues, right? And you could actually plot the spectrum of the eigenvalues, right? It would maybe look like this. I'm just going to make something up, okay? And that means some of the eigenvalues are big and some of them are small. That would be a typical situation. But okay, so then So when you compute x tilde E transpose x, that's the what's called principal components analysis, PCA. It's also in the continuous limit. If you have usually, if you're talking about a continuous time signal, so if x is a sampled signal, but a sample from a continuous time. In the continuous limit, it's called the Karhunen-Loew transform. And rather than spell this incorrectly, I'm going to actually look it up in Google. Karhunen-Loew. And please don't switch to the computer, because then everyone will see that I can't spell. Hold on. Karhunen. Loew. Loeve. Karhunen-Loew. So the Karhunen-Loew transform is the decorrelating transform for a random process, for a window of a random process. And PCA is, these are all the same thing. PCA, Karhunen-Loew. There's another name for it that you hear sometimes, but I can't think of what it is. There's at least 3 names for the same thing, okay? They're subtly different things. I mean, this Karhunen-Loew usually refers to the continuous time extension, and the PCA is, it often has the implication that you're going to do dimensionality reduction by throwing out some of the values with some of the components with small eigenvalues. Okay, but this is the decorrelating transform. So for a stationary random process, the decorrelating transform is the Fourier transform. That's the thing. So the Fourier transform is a good approximation to the Karhunen-Loew transform for any stationary random process. That's the amazing result. That's why the frequency transform is so important in compression. Could you give me any stationary correlated random process, speech, image, as long as you want to approximate it as stationary, then I could decorrelate the data by taking its Fourier transform, a frequency transform. Now, why is that true? Well, it's a complicated matter, and it can get pretty complicated. There's a lot of technical details, and there's various theorems and so forth, so I can't tell you exactly, but I can tell you this, okay? That let's say, let's say R, I forget, in this class, did we ever learn what a circulant matrix is? Let's say, okay, we didn't. Okay, so let's say R is the covariance matrix, R of ij. If it has the form f, some function, of I minus j mod n. Okay? So this is just means that it means like it's just like space invaders. Remember when I talked about space invaders? So Toplet's matrix, so this is the matrix R. If it has the property that the autocorrelation is a function which sort of wraps around. So it's a function here, and then it shifts like that, and then this would come out here and go there, actually. Right. So anyway, it has to be circulant. So if R is circulant, which means that the x is circularly stationary, okay, so rotations, its statistics are invariant to rotation, then you can show that R can be written as E lambda E transpose, where this is the DFT. And you know that's true because then this kind of looks like circular convolution, and the DFT turns circular convolution into multiplication. How many people know that? The DFT turns circular convolution into multiplication. If you took 438 or you took 538, you should know that, right? So because of that, the DFT approximates is a Karhunen-Loew transform. And now, okay, so this was a very long-winded way of trying to argue to you that the Fourier transform is the right thing to do to decorrelate zeta. So why am I doing a DCT instead of a DFT? Why not take a DFT or an FFT? Okay? Well, the FFT produces complex coefficients, but there's another problem with the FFT. The DFT and the FFT, I could just take, remember the FFT produces complex coefficients, but they're conjugate symmetric for a real valued signal. So I could just take half of them, and I could figure out the other half by just reflecting them. But the problem with the DFT is there's a more basic problem that occurs when the block size is small, okay? And it's a very important problem, so it's a first order effect, which is this. If I have some signal and it goes from say 0 to n minus 1, okay? And I'm going to take the DFT of this signal. And the signal looks like this. Okay? Oops, like that, right? And I take its DFT. I'm going to get the frequency transform of this. But guess what? That causes problems. Why? Because then the next sample here is n, right? And then that goes to 2n minus 1, right? But this thing starts down here again. I'm going to try to reproduce this. Okay? And then equivalently, this is like this. I'm not doing a very good job of drawing it, but, you know. So this signal has lots of edges in it, because every time it goes to, the DFT is assuming that the signal is periodic with period n. But this signal is not periodic with period n, not really. So when I come back, go from n to n minus 1, it's like, okay, you guys don't know what it means for a record to skip, right? Because you're not old enough to remember what those things were. But okay, it's like when you come around, it's like the tile on your floor. If it's not designed right, it doesn't repeat again. So this causes a sharp edge. Sharp edge. What's going to happen? What does the sharp edge do when I take the Fourier transform?
Delta function. So
when I take a Fourier transform of something with a sharp edge, what do I get? You're going to get a lot of high frequencies. And which was the part of the signal that was supposed to be 0?
High frequency.
The high frequencies. So this is going to splatter all kinds of energy into the high frequencies. So if you do that, these things won't be 0 up here. The DCT is just a variation on the FFT. There's actually more than one DCT. They vary very subtly depending upon how you organize things, okay? But basically, what happens is this. If you have a signal, I'm going to do it simpler this time. So you have a signal that goes like this, right? If you're doing so if you're doing an FFT, which is exactly the same as a DFT. An FFT is just a DFT that's implemented with a fast algorithm. So if you do a DFT, it looks like this is the signal, 0 to n minus 1, right? But it looks like the signal has edges in it. If you do it a DCT, what you're doing is you're taking the FFT of a signal, but what you do is you take this, so this is n minus 1, this is 0. What you do is you take this signal and you repeat it, but you reflect it instead of just repeating it. So you get something like this. So in this case, the second derivative, or the derivative's discontinuous, but the function's continuous. So you don't get a sharp edge. When you take the FFT of this, so you take the FFT then of this longer signal, which is now symmetric. When you take the FFT of the longer signal that's symmetric, what will happen is that you get twice as many coefficients, but now they're real valued because of the symmetry. So that becomes the DCT. So the DCT is basically assuming that the signal is reflected periodically instead of just repeated. So it's smoother, and you don't get high frequency noise basically splattered into the high frequencies because of sharp edges. this is a high-level explanation. Actually, my notes have some more details if you want to go through them, or you could just go to any number of references, including, I'm sure, Wikipedia, and it'll have a detailed explanation of the DCT. There's more than one version of DCT, depending upon some little details, like how you reflect it, if you repeat this point, or there's lots of little tiny things you can do differently, and there's about, I think, 2 or 4 different versions of the DCT, depending upon small parameters that you pick differently. So, but the basic concept is the same in all of them, that you just, you're essentially reflecting the signal rather than just repeating it. Yeah?
DCT also assumes that the signal is reflected. It assumes that it's reflected. So what artifacts it might cause because of this assumption?
Oh, well, I mean, you're still going to have a discontinuous derivative. So a larger block size still is advantageous because there's always some loss of coding efficiency at the boundary of the block. So, and also, well, in general, you'll get blocking artifacts also because you're ignoring the redundancy. Like pixels on the edge of one block tell you something about pixels on the edge of the next, right? So you could do things like you could have overlapping of the blocks, or you could decode this block and then use that to predict the pixels that you're going to code, and then just code the difference between the prediction and the actual values rather than just code the whole thing. So there's a lot of things going on here that are non-ideal in the boundaries. Simple, plain old JPEG just ignores all the dependencies across the boundary, and you get blocking artifacts. There's more advanced JPEG block transform methods that do a better job of handling these redundancies. But in general, a larger block size, well, for a stationary random process, a larger block size will give you better coding efficiency. For a real image, it may not, because the problem is the block becomes too large, and then you have stationarity. You don't have the texture, essentially, inside of a block may not remain homogeneous. So you don't have stationarity. And the Fourier transform is assuming stationarity of the process. Okay, so everybody understands the FFT, DFT issue here? And I think... yeah?
So why don't we just filter these high frequencies with a smoothing filter and then pass them through the DCT?
Well, because then you'll lose image detail.
Only high frequency.
Well, but you'll lose high-frequency image detail. I mean, if you knew that there were no high frequencies, you just subsample the signal at a lower frequency and just throw a lot of pixels away, right? But presumably the reason you sampled the frequency you did is because you thought there were some frequencies there, and they may not be as large in magnitude, but it doesn't mean they're not important. So, so there's information there. They're not all going to go completely to zero. I'm oversimplifying. It depends on what the size of the quantization level is. Some of them that are, even if you have a large quantization size, if you have a very strong signal, it'll be enough to get some output. So, yeah, I mean, so the high frequencies are important. They're not as important. And you wouldn't want to just get rid of them all. I mean, the logical conclusion of that would be just to transmit one pixel for the whole image. Just average all the pixels and just send one value, right? That's like the lowest frequency. But obviously you need more information than that, right? So, yeah. So the trick is it's really a rate distortion problem. You want to, for a particular rate, you want to get minimum distortion, or for a particular distortion, you want to minimize the rate. Let's see. I just want to go through here and see if I've covered everything. I talked about zigzag. Let me see. So, are there any other questions about the lab or the the implementation. There's some. I gave you in the lab. There's some specification of the general architecture of the code, and also one of the I think more challenging things in this lab is to manipulate individual bits. So you have to sort of build up a bit stream and then encode the bit stream. But so you have to be careful about that because you have to keep distinct in your mind the idea of what of a word, a binary word of data that contains individual bits you've set versus ASCII. If you encode ASCII, you're using 8 bits to encode, say, a letter. So you can use ASCII to encode 0 and 1, but that's 8 bits representing one value. So then you have to take that and compact it down to just individual bits. Because that saves 8 to 1 compression, right? You wouldn't want to lose that. So, and I think that's pretty much. So, are there any other questions about any other labs, or any questions about exam problems? Or any? Yep.
Could you explain this once more? Why should we have these samples as uncorrelated as possible in order to transfer it in less number?
I'm sorry. Say that again.
Could you explain this once again? Why do we have the samples as uncorrelated as possible in order to transmit it?
No, that's a very good question.
Less number?
So there is an answer to that question. There's a formal mathematical answer to that question. So I'm thinking about it because I'm trying to think of what the best explanation would be. Because okay, let me give you more than one answer, okay? You asked a very profound question, okay? So why is it better to decorrelate data before you encode it? So one answer is just that, well, it's more efficient to code data if the data is independent, because then the bits you spend, it sort of makes sense that it's more organized or something. I don't know. You can also actually argue that it's better to encode the data when it's dependent, because then you have redundancy. But it's kind of redundancy you don't have a lot of control over. Although people do things like that. And there is things like, for instance, techniques called multiple description coding and different things like that. So, but okay. So now I'll appeal to the following formula. Okay. So I told you that you take x, okay, and r here is equal to. So now I'm going to give you a formal reason. I don't know. Maybe it's too formal, but I think hopefully it's an interesting observation. Okay, we'll see. Okay, hopefully when I get finished, you'll be less confused, but I'm not guaranteeing that. Okay, so now you have r, and r here is equal to E lambda E transpose, right? So this is E transpose x. Okay, so that's x tilde, right? Okay. Now, let's say, so now if I code that, right, the rate, you know from the last class, okay, that the rate will be, I take, I take the variance. So define. Okay, so I'm gonna. I'll take the rate here will be equal to the sum from I equals 1 to p. Okay, of lambda I. So that's the diagonal element. It's the variance of the ith components. Because lambda I is equal to the expected value of x tilde I squared. Right. Okay. So that lambda I, and I divide that by delta. Remember the delta from last class, right? And I take that whole thing and I take the log base 2 and I multiply by 1/2. And that's the rate. Okay? Now if delta is less than the minimum, okay, over I of lambda II. If the distortion is low, so I have a small quantization step size, and this is small, then that's going to be equal to 1/2 of the sum from I equals 1 to P of the log base 2 of lambda II minus a constant. Okay, and the constant is 1/2 P times delta. Right? Log base 2 of delta. Right? This is a constant. So I can ignore this because it's a constant. And this is the rate. So the rate is this minus a constant, which depends upon the quantization step size, right? So the question is now, now it turns out, let's say that I take the structure of my argument is a little bit confused here because I'm making this up as I'm answering your question in real time. I mean, if I reorganize my logic, it might be a little clearer. If I take x and I multiplied it by, if I define x tilde as be t times x, okay, for some general transform t, right? If t was E transpose, that would be exactly the case we just considered. So let me start again. I'll say if I have x tilde is equal to t times x, right? And then I'd say, well, in this case, what the expected value of x tilde times x tilde transpose is going to be equal to t times the expected, is going to be equal to the expected value of t times x transpose times t transpose. So that's going to equal t times the expected value of x transpose times t transpose. So that's going to equal to t, and this is r, I'll put here rx, t transpose, okay? Now, in that case, so I'll define this thing here as r tilde, because this is the covariance of x tilde. So r tilde is equal to t times x, t times r times t transpose. Now, if I ask myself, well, what's the expected value of x tilde I squared, so the ith component, it's going to be equal to r tilde II. Right? So it's the ith diagonal element of r tilde. So in this case, the rate, so let's say I don't use the decorrelating transform, I use just some other transform or no transform, it's t. Then the rate here will be equal to 1/2 the sum from I equals 1 to p of the log base 2 of r tilde II. Right? So that's going to be equal to the same 1/2 the log of the product from I equals 1 to p of r tilde II, right? Okay, now, I know this is getting a little complicated, but bear with me. Okay, now, that means that I can write this, that the rate is going to be equal to 1/2 the log of, what I do is I take the determinant of the diagonal of r tilde, because that's by definition equal to 1/2 the log base 2 of the product from I equals 1 to p of r tilde II, right? Okay.
Now r tilde is not a diagonal matrix, right?
That's correct, but I took its diagonal, okay, and actually to be precise here, I should say minus 1/2 p times log base 2 delta, and this is minus 1/2 p times log base 2 delta, okay? But this is just a constant. So now I can ask myself, what's the minimum over t of the diagonal of r tilde, of the determinant of r tilde? And in fact, the value of t that minimizes this then would be the best t. Okay? So this is best transform. It's the best transform because it's the transform that minimizes the rate at low distortion. And maybe minimizes the rate at higher distortion. Actually, it minimizes the rate at any distortion. Okay? Well, no, we don't quite know that yet, but we will in just a moment, okay? But at low distortion, it minimizes the rate, okay? So this is equal to the argmin over t of the determinant of the diagonal of t r t transpose. Okay, well now I'm going to... At this point, I think the proof becomes unsatisfying, except for if you gave me more time, I could go off and even complete this, okay? This is the first part of the proof, but the second part I can't give you because, well, maybe I could. I'd have to really wing it, okay? But the solution to this is well known, okay? And the solution is, T equals the eigendecomposition. Now, how do I prove that? Well, I'd have to go back and... I know I've proved it before. I've even proved it before, okay? But I'd have to go look at the proof. I'd be afraid to try to prove it right here without any preparation because I'd probably go off on some weird tangent, okay? But believe me, it can be proved that that's correct. So I'm not sure I answered your question, but I posed the question in a different form, which is I said, so minimizing the rate is equivalent to finding the transform. This is sometimes called a similarity transform on R. Finding the transform of R with this, finding the T, which minimizes the product of the diagonal elements of this matrix. And you can prove that the T that does that is the eigendecomposition. Okay, but now I can't prove that for you, but I can give you a motivation that's very strong based on a picture. Okay, so here's my picture. Okay. Here you go. And okay, I just thought of it right now, and it's good. Okay, so we'll do this in the two-dimensional case. This is x1, x2, okay? So let's take a Gaussian random process, right? So it's got some general... the distribution is the contours of the probability density for a multivariate Gaussian are ellipses, okay? So it's just some ellipse. So an ellipse is defined by its by its axes, right? Its eigenvectors. You know this from the lab. Okay, so it's like this. And it's zero mean, so it's centered, right? And this is the first this is eigenvalue 1, and this is eigenvalue 2, okay? It's either that or it's 1 over this. I have to think about it. I think it's 1 over this.
1 over.
Okay.
Maybe square root.
Square root. Thank you for saving me from myself. My answers are never completely wrong, but they're usually not right either. Okay. They have the general... You have to extract from them the truth. Okay, so... Okay, now... This is what's happening. Okay, if I ask what's the determinant of the diagonal of this matrix, this is the question I'm asking, okay? Are you ready? This is very cool. Okay, just a minute. I'm going to draw this one more time, okay, because I need a little more space. So I have, this is x1 and this is x2, okay? So this is the ellipse. If I ask what's the volume if I ask what's the determinant of the diagonal elements, okay, well, I'm taking the product of the diagonal elements. When you take the product, the diagonal elements represent, let's take the inverse covariance instead of the covariant. Let's make this the, this needs to be the lambda ones. Okay, so it's not the, it's just that shape, okay? Okay. Now, so when I ask you what the determinant is, the diagonal elements, the first diagonal element is the variance of x1. The second one is the variance of x2. So it's like I put this in a box, and I asked you how much volume was in the box that encloses it. Now, if you give me a football, okay, now anybody knows the answer to this question, okay? If I have a box, and I want to make the box minimum volume, and you give me an American football, the only true football, okay? Now, are you going to try to take that football and stick it in sideways? No. Nobody's going to do that. You're going to take the football and put it in this way, right? So therefore, any ordinary person knows that the transform that minimizes the determinant of this diagonal matrix is got to be the eigen decomposition. Everybody knows that. Because everybody knows that when you put a football into a box, you always have to line it up with the box in order for the box to have minimum volume, right? Because otherwise, if it's cocked sideways, it's going to push the sides of the box out, and it'll take up more area. So that's the answer to your question. I'm sure it involved all kinds of concepts that you didn't expect it to. Okay. All right. Any more questions? That's actually a very fundamental question. It's a very, very fundamental question. Why is it? I mean, it's a very fundamental question because coding of data is a very fundamental problem. Because if you code data properly, this is why quantization is a very fundamental question, because it asks what in data is most important. And if you can separate out the most important information from the least important information, you can do something that's very fundamental, okay? And so the optimal way to code is to decorrelate first if you can, or to make actually independent random variables. But it has to be decorrelated with an orthonormal transform. If you can decorrelate the data with a non-orthonormal transform, maybe you can put the picture on me because I'm not going to draw anything for a while. If you can decorrelate with a non-orthonormal transform, well, the problem with that is that, well, you've decorrelated the random variables, but distortion in one dimension is not the same as the other. See, maybe we'll go back to the paper. If you have x here, and you put it into an orthonormal transform t to get out an x tilde, any distortion here in mean square error here is equal to mean square error here. But if this is not an orthonormal transform, if it's a nonlinear transformation, or if it's a non-orthonormal transform, then the distortion in this domain may be different. So therefore, you quantize at your own peril, because it might be that a small error here becomes a huge one there. Right? So Gaussian random variables are a special case, but an important special case, in which you can find a single transform, you can find an orthonormal transform, which will completely decorrelate and make the variables independent, so that they can then be coded. So the standard rate distortion theory starts off usually by making the assumption that the thing's Gaussian and multivariate, because that's a case you can handle easily. Of course, in real data, that's not the case. You can decorrelate a real image. There are transforms, linear transforms, that would decorrelate the image, but the result will not be independent random variables. For instance, if you take something like a wavelet transform, I have 28 seconds left. If you take a wavelet transform of an image, you'll get stuff that looks, you'll see the edges, the outline of the image, because it's uncorrelated, the variables, but they're dependent. So, okay, so it's a nice concept perhaps to end on. And I apologize for the off-campus people that didn't get any candy. And it was fun, and see you again next year.